We're going to talk now about the force of friction. Friction is something that we've done our best to ignore so far in this course, and we've largely dealt with idealized or somewhat theoretical situations where we have smooth, perfect surfaces that don't have friction, so that we could do some visualization of Newton's laws where we wouldn't have to deal with the complication of friction, which we normally have in the everyday world. In the everyday world, of course, surfaces are not smooth, they're rough, and as objects slide along one another, the rough parts of surfaces catch and cause friction. That's why we get to do things like light a match, because without friction we can't generate heat and we can't do things like light matches. But our effort to visualize these ideal surfaces and these idealized situations where there is no friction have even caused us to resort to thinking about problems in outer space, where when we push on a spaceship and give it a push and then let it go on at constant speed, we can neglect things like air resistance, which is a form of friction, or even surfaces to slide on, which cause friction. All so that we can imagine these situations where Newton's laws apply without too much complication. That's not to say that Newton's laws are not true here on Earth. It's just that actual problems that we need to solve, and we'll begin to solve from here on out, deal with extra complications in that the forces that we must consider include one more in the list. There's not only going to be forces from a push or a pull or from a tug on a rope or a force of gravity, but now we're going to have to start dealing with this force of friction, which isn't something that one can see just by looking at the situation. One knows it's there, and one has to start plugging it into our equations. Real surfaces are rough and cause friction, and as a result we're going to have to now add another vector into the equation for Newton's laws. That's okay, we can still come up with correct solutions to our problems. It's just that when we draw a free body diagram and eventually write down Newton's second law, there's going to be one more term for the list of forces that act on objects. I have to say that our language about introductory physics is sometimes confusing. We say things like an idealized world or an idealized model, which does not include friction. It's not to say that friction is something that's not ideal in the sense that it's a regrettable thing that we have friction. By idealized, what we really mean is that it's a simpler model to describe if we don't have to do this one extra term for friction. In fact, friction is quite important to us. There are a lot of daily tasks, like walking, that we could not do if there was not a frictional force between our foot and the ground. And as we know, when it's slippery out or when it's icy, we tend to fall because there's not enough friction between us and the ground. And we hear about in the news, at least in Texas, those drivers up in the north who end up sliding around as they try to take a turn because there's not enough friction restoring their car as the car tries to take a turn. So friction is not a bad thing, and what we really mean when we say idealized is that there are calculations we'd like to do, and these calculations are a little simpler, and we can make a slightly easier simplification of some equations if we get to ignore some terms. The correct description then requires us to put back this thing which we might have wanted to ignore because it is a little easier, but our intuition about how Newton's laws work just work fine as long as we include one more force in the list of forces. Friction, though, is a major source of confusion for a lot of students because our experience about force and motion are somewhat at odds with the statement that an object in motion will stay in motion and an object at rest will tend to stay at rest unless acted upon by a force. The graph below might try to visualize what happens when someone kicks a soccer ball and it rolls along in the grass and slows down because of friction and then ultimately stops in a net. We know that the ball slows down because of friction, at least that's what we're told, but many times we tend to think about these problems as if there was a force given to the ball, and unless we keep pushing on the ball, it will slow itself down, as if to imply that one needs a force pushing something forward in order to sustain the motion. That's very much at odds with Newton's first law, which says that once you give it a push and it is in motion, it should stay in motion unless acted upon by another force. So in time period C, the thing to impress upon ourselves is that it actually is being acted upon by another force. That's the force of friction. And yet, when people are asked, when is it that the force of the girl and her kick is acting on the ball, they tend to respond both B and C. It's just that in time period C, so many people say, the force of the girl is running out, confusing the notion of force, which was taking place back when her foot was in contact with the ball, with the idea of energy, which we've yet to talk about in this course, which in fact does get dissipated away from the ball. As I say, this is a confusion because it goes back to some misnomer about how motion really works, and the misguided thought process is that one needs a force pushing forward in order to sustain motion. If we analyze this sequence of events properly, we would realize that in time period A, there is no force acting, and so speed is constant. In time period B, there is a net force, and by Newton's second law, there would be therefore a change in speed, or an acceleration. The net force is in the forward direction because it's the sum of the kick going forward and frictional force going backwards. And time period C, there is no force from the girl anymore, so there's only a frictional force which points backwards against the motion. And since it points backwards against the motion, it causes an acceleration, but a negative acceleration or a deceleration, a slowing down. That's a little bit like time period D, when the net is the thing that causes the deceleration. If we realize that there are forces taking place in both time periods B, C, and D, then the change in speed in these different time periods is not so confusing. Here's a question that sometimes gets at the heart of how we are confused about how friction works. Suppose you're pushing on a couch and you're trying to move it along the floor, but it does not move. Which of the following statements explains the situation correctly? Is it A, that the inertia of the couch is greater than the force you apply? B, that the force of friction is greater than the force you apply? C, that the forces on the couch are balanced to equal zero? Or D, in order to have the couch moving at a constant speed, it is necessary to be pushing forward with a greater force than the backward force of friction? Many people would respond to this question by circling items B or D, but those are not correct. Both B and D indicate an unbalanced force, and you would not have an unbalanced force unless you had an acceleration. In this problem we're asking, we would just like to push the couch forward at constant speed. In fact, the correct answer here is C, that in the time when you're not able to move the couch, the forces on the couch are balanced to zero, and since they are, there's no change in speed, and what was formerly at rest remains at rest by Newton's first law.